Yes, I think we have all the technical setup ready. So I believe we can slowly begin our session. So I will ask Christian Gauer to chair this session and introduce our speaker, distinguished speaker of today.
Okay, can you hear me?
Yes, please.
Wonderful. Welcome everybody. Thank you for being with us and welcome to this session. It's my great pleasure to announce Professor Geoffrey Fox from Indiana University as our keynote speaker today. For most of you, Professor Fox will not be an unknown. He has been engaged in the development of software technology over the past 4 decades, not the least in parallel computing. He has made many significant contributions, far too many to give them justice here. So let me briefly mention a couple of aspects that touched on my own professional life. I still remember Professor Fox's push for the Java Grande Forum in a passionate talk at Europar 1998 in Southampton. It was one of the most passionate talks I ever experienced. Java Grande was an effort to make the then young programming language Java more suitable for high-performance computing. Since the turn of the century, Professor Fox was engaged in the promotion of cloud computing and its applications with diverse projects, publications, and appearances. A few years later, he was early in recognizing the significance of the MapReduce paradigm, which he promoted again with implementations and many publications and with a dedicated workshop series. Today, Professor Fox will be talking about one of his main interests and battlegrounds, the convergence of HPC, big data, and machine learning. Professor Fox has received many distinctions, the most recent being the ACM IEEE Ken Kennedy Award of just last November. Today, we are happy to add one further distinction, namely the Europar Achievement Award 2020. This award has been conveyed every year since 2008, so the Europar Hall of Fame is now 13 strong. And you can view its members on the honors page of the Europar website. I will enter Professor Fox there right after this session. To qualify for the award, you have to have shown a special allegiance to the Europar conference series. Professor Fox's contribution here is especially significant. As the editor-in-chief of the journal Concurrency in Computation, Practice and Experience, he has supported and governed the so-called Europar collection in this journal, the best Europar papers of the years 2007 to 2016. I was the chief guest editor of this collection, and I'm very happy to state here that I have never experienced a more easygoing, efficient, and supportive long-distance interaction with anybody other than with you, Geoffrey. It was a real pleasure working with you, and all people who know me know that I'm not making empty compliments. Typically, the award winner is invited to the conference and celebrated at the banquet with an honorary plaque. Sadly, this year we had to mail the plaque instead and can only show it by picture. But I keep up my hopes that there will be an occasion to celebrate you personally next year in Lisbon. For now, I'm eager to hear what you will tell us. And as everybody else who is listening, I'm very much looking forward to your talk. The screen is yours.
You need to stop sharing.
I'm not the one who's sharing. It's the organizers are putting on this.
I guess the organizer needs to stop
yes,
sharing.
Yeah. We can look for the flag, and now we switch to the presentation.
Okay, thank you very much for those kind words, and I'm very happy to come back to Europar again. And I'm going to talk about several things and explain why I think, while I was passionate about Java Grande, while I'm possibly equally passionate about these topics here. we'll skip the abstract. So if we look at this field we're working in, it's changed quite a lot. When I started doing parallel computing, which was unfortunately 40 years ago, all aspects of it were very vibrant. They were at the leading edges of computer science. Every computer science department had an IPSC2 in the US and a transputer in Europe. And then after that, things have changed a bit. So initially, hardware became hard in universities. And then maybe the parallel algorithms actually were so successful that they didn't have so much work. There's always has been and will be work in software because it's so hard and unsuccessful in some fashion. And also high performance computing thrived. And then if you look at today, things have changed, and they've mainly changed due to big data and deep learning. You can evaluate this change, and I've done that in other talks with conference attendance and citations and things. And you will find that at least some areas, including high performance computing, have become much less, seemingly less exciting academically. Even though HPC is now incredibly important, it's far more important than it ever used to be, as is parallel computing, because all of industry depends on it. However, the people somehow HPC has become engineering, not research, and there are few academic opportunities. But as I hope in this talk to show you, there are lots of things to be done. And actually the algorithm area, which is applied math and things like that, that is really thriving, both in deep learning and the integration of deep learning with more traditional simulation applied math. One thing which I think is, maybe I'm wrong, but my impression is that deep learning is replacing almost all other forms of machine learning, at least for large jobs. And somehow that feature has not quite been recognized by some activities. Also, when we look at parallelism, as I'll show in the next slide, there is lots and lots of synergies between parallelism in big data and parallelism in simulations, but there are some important differences in that I don't think big data problems are quite as big in terms of number of nodes or simulations. At least that individual jobs aren't. That's because the amount of people are running lots of modest sized jobs, not so many few giant jobs as they are with simulations. So if we come now back to the convergence, I've already pointed out that high performance computing is essential. You can't do big data without HPC, and you can't do big simulation without HPC. And the examples are obviously the exascale computing initiative, the broad success of computational science and across simulation, and also the use of HPC and especially GPUs for deep learning. Now, Dean gave a very important talk in 2017 where he pointed out we have systems for machine learning and machine learning for systems. So using GPUs for deep learning is using systems to advance machine learning. And more generally, I call that HPC for machine learning. And it's relatively clearly very important. And as we started off, we should mention, we started off working on MapReduce and how to run that very fast. That is now, I think, relatively clear how to be done and what needs to be done. There is some lack of clarity because some things are called supercomputers, some things are called clouds. And nowadays, it's not quite so obvious there's any difference. And another interesting area which I worked on was seemingly, it doesn't seem to quite work. Namely, it's sort of obvious that most of the best software comes from the Apache Foundation, and yet that is not very well integrated with simulation field. An area which I've worked on recently, Dean called machine learning for HPC, where we use machine learning to enhance the HPC. I would view that as extremely important, and there are lots of research areas, both algorithmic, hardware, and software. This is an old slide which I often show, which points out that if you look at applications labeled maybe by the amount of data and the synchronization, then actually both big data and simulations appear all over this. At the most complicated place on the far right, we have classic complex simulations with adaptive sparse algorithms, but you also have graph analytics and latent Dirichlet allocation, which are pretty sophisticated big data problems requiring pretty difficult parallel computing, especially that graph case. Graphs are can be very hard. Then we have in the middle the sort of heart where HPC is thriving, which is GPUs for pretty regular deep learning applications and GPUs for molecular dynamics and things like that, which are hugely successful. Then on the right, we have loosely coupled, which is probably the dominant industry application for big data, which is where MapReduce thrives in its sort of traditional fashion, running lots and lots of jobs. And that's because, why is there so much interest in this field? Well, that's because there's 7 billion people, and all of those access the cloud. Well, not a large fraction access the cloud, and so there are lots and lots of independent jobs. And of course, there are also parameter sweep simulations in this category. We'll come back to data engineering. I just wanted to note this famous paper from 2015, NeurIPS, and it points out that the machine learning, if measured by lines of code, is a tiny fraction of the available code. That was true then and is true today. And we need to understand how we link these different parts together. We'll come back to that at the end. And they actually live in different worlds. The machine learning is Python and C++, and this other part, a lot of it is Java. And although people point out this nice diagram, there's a pretty important conference, MLSys, which is the interface of systems and machine learning. I looked at every paper from the 2020 conference, which I went to, and I think essentially they're all in this red area. So there's certainly, it may be a small part of the code, but there's plenty of interest there. Okay, let's just look at machine learning for HPC and surrogates. So this is work I did with Shantanu Jar. I published a couple of papers which are already totally out of date because there's a lot of progress here. And here the machine learning is used to enhance simulations. And this is one interesting part of this field is they're very application dependent. It's pretty hard to make progress in using machine learning to enhance HPC by just looking at HPC. You really have to look at the applications. I personally think more work needs to be done in collaboration with application people in this area. So Shantanu and I divided there are thousands of papers, maybe tens of thousands of papers in this area. And if you look at them, they fall into three broad groups. The first group is famous, say, for auto-tuning, where you might use more sophisticated machine learning in your auto-tuning. The second group is very active, which perhaps the most important is smart ensembles, how to navigate through phase space in an efficient fashion to fold proteins or find important drugs. That's all been revolutionized by machine learning methods, as has finding potentials and things like that. The third area, which is the most direct, is you just replace your HPC by a deep learning network. You just learn to instead of running your PDE solver or ODE solver, you just hand the inputs to a neural net. Those are called surrogates. Here's work I did with a student, JCS, and Vikram Jadeo, a faculty member at IU, and it is in material science, and it's similar to many such papers. And you just replace the LAMPS molecular dynamics code by a neural net. The neural net's actually a simple dense network shown at the top right, and it has an interesting feature that the speed up is 10 to the 6, although that speed up of 10 to the 6 only is true when you've run it so many times you don't have to put in the training time, because the training time requires running, in our case, 5,000 simulations to get the training set. So this is particularly important for cases where you want to run lots of jobs. So there are two good examples of that are education, where we put this on NanoHub. Also, General Electric gave a talk at a meeting I was at recently, where they they specify a CFD problem for their engine design. They run 200 training set values, and then they use the neural net to allow the engineer to continue working interactively during the day. So here we're replacing a complex simulation by an immediate lookup. And so this factor of 10 to the 6 is directly applicable. Of course, here on the bottom right, we show the comparison of the neural net to the HPC simulation. And I wouldn't be giving this talk unless they were pretty good y equals x straight lines, which they are. They aren't, you don't get, I mean, one of the challenges is to understand what the size of the training set is, what the neural network architecture is, and for different applications. There was a famous paper from January from United Kingdom, Oxford, which had the interesting title with claiming a speed up of 2 billion. And they use interestingly, a totally different network, and also they use techniques which automatically learn the neural network as part of their hyperparameter strategy. And they did 10 different cases. They took one of them, a slightly obscure one, to learn the network, and then used that for all the other applications. And the reason they got a speed up of 2 billion, they only had 39, one of the applications was climate, for which they only had 39 applications. And so the speed up there was enormous. Here's another random example I found last year from the web, which showed that this company has INSILICO medicine from Hong Kong was using commercially AI, this type of surrogates to discover drugs, because you can use these surrogates to either map, to replace HP simulations or to replace chemical property lookups. And the claim is they did for $150,000 what would normally take, and a few months, a handful of weeks, it says, maybe a couple of months, and it would normally take 7 years and $2.6 billion. So I think this whole area is pretty important. And that some of this type of work is going on for COVID at the moment. Here I now want to slightly generalize this from you could call this an applied math point of view. And so if you look at solving, if you look at, say, that material science problem. So there we have the classic application of coupled differential equations. It would have the new value, you evolve in time, and the new values of the differential operator times the previous values. Well, it's sort of worth noting that the deep learning is actually pretty similar. We have some previous values, and then we get some new values. And so deep learning provides a way of generating new operators. And the interesting thing about these operators is they're totally different from the ones I was taught about 50 years ago by Maurice Wilkes at Cambridge. Namely, they've really got lots of parameters, possibly hundreds of thousands. And we were told never to use more than a few parameters because high order approximations were so unreliable. So I think it's sort of interesting to explore the deep learning from this point of view of new ways of doing operators. Here is an example I did again with JCS and Vikram, where we used not a dense network, but a recurrent neural network to actually predict the evolution in time of particles moving in the potential here, in this case here, the Lennard-Jones potential. And these four plots here are 4 views of the simulation. This one here is actually identical, but it's 4 views coming from the neural net. And the surprising thing about this study was that if you look at classic, these simple approximations that Maurice Wilkes told me about, you you have to have a very small step size, 0.001. And if you increase the step size, the error gets huge. The factor gets to 10 if you multiply the error by 10, the step size by 10, or if you multiply the step size by 100, it just explodes. If you take this learned LSTM network, it is completely robust up to a time step of 4, even though it's up to very large times, much larger than the training time. And that's shown here at the bottom right, where we have the error is not 10 or 10 to the 23, it's 10 to the minus 5. And this is dt of 0.1, 0.4, 1, and 4. And notice it's stable as a function of time. And as I said, this particular case is 65,000 parameters and 5,000 a training set of 5,000. And here's the similar results for different potentials. And here we have the error for 0.01, 10 times the the normal steps, the recommended step size for classic ODE simulation. Here we have the step sizes of 0.1 to 4 for 3 different networks, and they get good answers for all 3. All right. I'm working with a colleague here at IU, James Glazier, on trying to use this method for agent-based models, where we can actually replace the agent by surrogates. And we have some vision of actually being able to do what are called digital twins, models of organisms which are automatically generated using these neural network-based surrogates. And that's work in progress. But this idea has lots and lots of applications, and I think we ought to ask, what can you do with a factor of, well, either 2 billion from Oxford or 10 to the 6 from us? So this one slide summarizes that field, and it's broadly used, but it's non-uniform. So the use is broad but non-uniform. It's particularly well explored in biomolecular simulations and material science. It's not so well explored in other areas, such as the agent-based case I mentioned. And the multi-particle potentials are extremely well successful. That's used a lot. The collective coordinates and the smart ensembles is very successful. It's also used for things like clouds and turbulence, learning microscale. I mentioned the recurrent neural nets. The 2 areas I'm working on now, sort of from, if you like, an applied math point of view, is trying to learn not just the values, but the errors, because you should estimate the errors as well as the values from your neural net. And perhaps more importantly, how do you design the neural net and the learning process, the active learning, so you minimize the number of expensive HPC simulations? Here I say the 2 billion, the paper with 2 billion in the title was interesting because it got away with less than 40 simulations by using this learned network. I'm not certain. I think we need to study that more deeply. All right, so here is a totally different part of the talk, looking at deep learning with COVID distributions. And this is motivated by that surrogate work, is we're trying to derive an operator. You see all these nice plots of the number of COVID cases and things as a function of time. Well, we would like to find an operator that was able to understand and reproduce and predict, forecast those results. And here the data is the counts of infections and fatalities. And now we actually think this is an important point, which is that needs, I think, a little more study. Because if we think about the Leonard-Jones potential, its operator depends on the parameters of the potential. So when you have an operator, it has some fixed parameters or properties which go into that operator. So in the case of COVID, those properties are things like the number of hospital beds, the percentage of people who are seniors, because we know that impacts the progress of COVID. And so in order to describe data across many locations, we're going to need to put in these properties. And I'll come back to this model from the University of Washington, but I use that as just a way of measuring how well we do when the data is very smooth. Let me just show some results. So this is actually, I actually just got some new data a week ago. I haven't had time to update it. But here we have, I'll describe the model in the next slide or two. But here's a typical result. So here is the data until May 25th. And this particular model predicts 2 weeks into the future. And the amusing thing about this deep learning is it's completely dumb. It predicts what you train it on. So as we know, people do not get infected or do not die on the weekends. And if you look at the data presented by Johns Hopkins and other places, it's got huge weekly oscillations in it. And this prediction learns those weekly operations, even though it's probably fake. It's probably due to the reporting issue, not to the actual issue. So anyway, we get pretty reasonable answers here. The red here is the error, the blue is the prediction, and the orange is the data. This is data summed over 110 cities, and we sum the square root of the number of reported cases, because if these were this should be a counting experiments which with errors go like square root of n. And so in order to get the correct loss function, you ought to take a loss function, as far as I can see, which is the square root of the number of points, number of observations. Let me try to do this a little more generally. So there's lots of problems of this class. Earthquakes, when I mentioned new hydrology, where we have a set of space points which may not be near each other. They look near each other on this plot, but they may not. In the case of COVID, we had 110 cities across the horizontal axis, but they were not particularly near each other. They were scattered over the US. And then we have some time, which in the case of COVID was 115. And so we have observations at these blue points, and then we can do two things. We can forecast the future, which is what I just showed, or we can do what's called a sequence-to-sequence map and forecast the same time. In the case, this type of problem is seen in is actually best developed in natural language processing, because that's where LSTM and those architectures came from, where the space points are different paragraphs or maybe different books, and we have along the time axis sentences, and we're trying to translate from English to French in this direction. So the basic mathematical problem is you have a set of windows, those are the time sequences. You have properties of those windows, and importantly, these properties are static and dynamic. So this is the basic ODE operator. And we have time-dependent things like particle position and particle velocity, and we have static properties like particle mass. And we want to forecast the future, and which could be well into the future, and we want to predict things now. All right, so that's the general problem. So I'm trying to solve this general problem, and there is no clear discussion I have in the literature from this point of view of looking at operators to describe these space-time properties. So if you look at this, the simplest thing which I actually showed you in a couple of slides ago is the LSTM, where you have a couple of layers, some initial dense layer and a final dense layer. However, if you go and just browse the literature, you will find that such networks have fallen into disuse in natural language processing and related areas. Rather, people use it. There's a famous paper saying attention is all you need. And what is attention? Well, attention is actually patterns which are cross space and time. And those patterns are expressed mathematically as linear combinations done by neural network layers of the points of one space-time set of data, and you compare that with other space-time sets of data, and you learn patterns. And so that's what the attention model is. And you have so-called multi-headed attention, which means you learn many patterns. So we have also, this is sometimes called a transformer model, and the normal transformer model is done for sequence-to-sequence map, and it's some sort of a classification, because you're not trying to predict a continuous, if you're doing English to French, you're trying to predict a particular French word, not a floating point number. Here we're trying to predict floating point numbers, and so that's most natural with the LSTM. So here we use attention to effectively gather more data for the LSTM. Then we merge that into the LSTM, and that's called the encoder, and this is called the decoder. And so this is the hybrid model. And the hybrid model, as we'll see in the next slide after this, is even better than the LSTM. And again, if we look at applied math, this is really bizarre. I told you to put in the static properties. Well, you also put in cos theta and sine theta, where cos theta is the angle which runs from 0 to 2 pi, so it has 7 values over 7 days. And when we're going to do annual things, we'll run it to 0 to 2 pi over 365 days. And that is much improved if you use these temporal or positional signals as your input data. And again, that's not something I learned from Maurice Wilks. And another important feature is, which I learned recently from playing with this model, you should shuffle everything. You shouldn't use, I thought you should start off looking at looking at a fixed time and all points in space, but that does not give anywhere near as good an answer as totally random points in space and time. And let's come here for this plot here. So this is this transformer. And these are even better. These plots are significantly lower in mean square error. And this model trains very efficiently. Every now and then, of course, when these stochastic gradient descent optimizers have a little mistake. This one had a mistake, but I just did that for fun. But anyway, these plots here at the top show here the cases and here the fatalities. And we have the predictions. And this is about 30% better in loss, which is the square of the error, than the pure LSTM. And so I'm trying to apply this now to lots of other cases. And let me just skip that. So what have we learned here? Well, we've learned we can derive operators. And we had this example of the current neural net operator. And we've now shown that you can actually derive operators which have both static properties and they input dynamic variables and output dynamic variables. And those operators can be learned in the same, essentially the same way the operators for Newton laws were learned. And there's lots of questions here. I pointed out that we had the recurrent neural net, which we did for Leonard-Jones potential in the COVID case. We had convolutional, which we did in the Oxford model for surrogates. Dense and the material science application we did here. The transformer, which I just showed you for the COVID case. I will mention briefly earthquakes, and there we use the so-called convolutional LSTM. And for all of these, we have hyperparameter choices. And we also, I think, need a little bit of thought about how these static variables are treated. At the moment, I am feeding in the static variables. I think this is what most people do, as though they were ordinary variables. So the time series just has a property attached to the time series, which is unchanged in time for, say, the percentage of seniors. There possibly is a more elegant way, but I don't think you want to separate the static properties from the dynamic properties, because we again think of Newton's law. Mass, this was a static property, or the strength of the Leonard-Jones potential, they're built into the operator. So I think we need to build the static properties into the operator, but these deep learning networks are so flexible. You can do anything. So I think it's important to study this. I will come back to MLPerf, but the MLPerf is a very important organization, and they're also extremely interested in time series. Actually, this is where my interest in time series first started, and they have collected together a huge number of areas: transportation, medical, cybersecurity, social statistics, finance, science, software systems, language, IndyCar racing. This is my colleague Judy Chu. She is using this to predict who's going to win IndyCar, and social media, Twitter. These are all time series, and we need to understand how best to do them. And you can here's the model, which has various different forms. So we need to generate an I think it's not very well understood what to do when, and I would like to generate some benchmarks and exemplars across these areas so we can see what works when, and then give insight to people doing new work. As an example of a work I was doing this summer is I just happened to look in hydrology because some of my students from an undergraduate research program were interested in climate change and related area, environmental science. And actually there was a survey paper which published 129 deep learning papers. And they have a wide variety, as you see on the right, of different methods. So there's lots of methods applied. I looked at about 10 of them, and I don't think any of them use what I would consider they were not wrong or anything, because they used perfectly correctly networks, but they didn't do what I would consider to be the best practice use of the choice of hyperparameters and things. And so again, that's another motivates me to try to produce some well-established exemplars and some challenges in terms of benchmarks. Here's a very quick, I will do this quickly, earthquakes. This is actually what I started doing. In earthquakes are actually hard because they are phase transitions. And so if you think about deep learning is trying to find the hidden variables. And as far as I can see, if there are hidden variables like the dynamics of Leonard Jones, it will find them. And so when my colleague John Rundle from UC Davis gave us a model for an earthquake, we found it immediately. However, the real data is not at all so clear. And possibly the reason is deep learning will not find totally random events because there's no hidden variables. It's just generate random number between 0 and 1 and decide to have an earthquake. That's not going to be predictable. So we'll have to see. We're still working on this. But I think it's important to note that it's good to have some understanding of what the hidden dynamics might be. Here's this discussed here. So if we look at earthquakes, they actually form one of those space-time problems, which I just discussed. And it's certainly true that the people who use simulations to predict earthquakes find it very hard because of this uncertainties, and that the simulations are pretty uncertain because you don't know enough data on the fault, the laws of friction and the faults to do a reliable prediction. So it is possibly the only chance of predicting earthquakes is to use a data-driven method, because the data that you observe does have embedded in it all the information about the faults. The only question is whether that data is even enough to do anything. So we'll see. It's pretty challenging. You have faults which differ in minutes, the aftershocks from a big earthquake, to the difference in time between earthquakes, big earthquakes, which can be centuries. And another amusing problem is what you use, whether you use energy. Well, energy sounds natural because life is nature, Mother Nature conserves energy. And so it's presumably a pretty important variable. But what you always use is the magnitude, which is the log of energy. Now we're going to put this in a neural net and multiply these things by matrices. So it means we're doing arithmetic on the magnitudes. Well, that's sort of strange because that's multiplying the energy or something. So it's that's another, there are an extra set of problems like this as to how sensitive, what the right variable is, because you need to, if you're going to use activation layers, you need to keep the magnitude of the variables inside the neural network under control. You can't have 10 to the 7th variation in magnitude and get good answers. And so that actually, it was helpful to me that I wanted to take the square root of n in the COVID problem, because that actually reduced the range of data significantly. Anyway, and this another important case here, this actually looks like an image, because the points which I have data from for earthquakes are spatially nearby. So we were looking at Southern California. I'm also looking at more traditional machine learning here. And here is the region we were looking at. Ignore the red boxes. They're just 5 big earthquakes that happened in this time period from 1990. And so we took that space-time model and applied it to this space-time. And I only have very preliminary results, partly because my student went to work for big industry over the summer. That's also my students work for industry over the summer, at least most of them. And I would point out the convolutional LSTM, that takes an LSTM and does various convolutional or dot products for the matrices. And we actually have improved that as part of this work, and that gives better answers for the performance of the predictions for earthquakes, but I'll describe that at a later time. And you get plots like this. Here we have 2 examples of predictions. The true is the actual values, the pred is the predicted values. They're certainly not perfect, but they're better than a monkey predicting it. So, and that's with this convolutional LSTM. So that's yet a different thing we can use here. And I should point here that this plot here is the earthquake faults, which is in Southern California. That's these red bars here. And this sort of suggested to me we could use graph neural nets, because in the corresponding traffic problem, which I think you might even have the talk on that, you often use graph neural nets because the highways are connected in a graph. And well, we ended up not doing that, but we may come back to do that. And rather, we just joined together the space points into groups, and we had some 100 groups which are noted in these color sets. This is the groups of nearby earthquakes. And so we're trying to look and see whether that's a good idea. We will see. So now let's come to benchmarking. So I should add that this whole area of spatial, geospatial time series and spatial time series and surrogates, which are effectively time series, is very promising. Lots of interesting work to be done, both in lots of applications. Every simulation can be looked at. Every environmental science data source can be looked at. So we now come to MLPerf. So I started, every now and then, I just randomly do something. I remember I've been working with NIST for 7 years because I went to a big data online get-together that they announced, and I'm still working with them. So I just came across MLPerf and went to their working groups. And MLPerf is pretty interesting. It has 73 companies, 10 universities. It has 50 FTEs working, average over these companies and universities working on MLPerf. It has pretty interesting working groups. I mentioned the deep learning for time series. There's a big HPC working group run largely by the Department of Energy Labs. I would like to encourage your interest in the science data working group, which was led by Tony Hay from the UK and myself. And we're trying to build benchmarks across different application areas. Now, as this was done by industry, who of course is a pretty important player in all these areas, the benchmarks here, which are illustrated in this, and this is actually training versions 0.7, not 0.6. I don't know why I mislabeled it. And no, this is 0.6. I should have updated this slide. Anyway, it has a set of 0.7 has a better recommender engine application. but it has otherwise the same. There's translation, imaging, reinforcement learning for the game of Go, and recommender engines. And then we have established, we have open data sets, we have reference implementations which are open, and then people do new implementations in various challenges. And these is pretty exciting HPC. Here we have 200,048 TPUs. That's well, that's this one here with two TPUs per node. This one here, and we have 1536 down here, Tesla V100s. And I say I should have updated the version 0.7, which has updated NVIDIA equipment and updated Google results. Anyway, this is a rich source of information, and all of this data is open and gives you examples. There are lots of good examples here. ResNet, Coco, Transformer, which I was just discussing, they're all there. And for the new recommender engine, they have DLRM, which is Facebook's open source, really top class deep learning recommender engine. Let's skip this. So I propose that we do this for science data, because there doesn't seem to be such a vibrant, broad scientific data activity. An industry has established a set of processes and a set of working groups, which we should try to copy. And so I persuaded Tony Hay and Yehan to join me. And we hope to generate a benchmark suite covering these different areas. We will work with the DOE HPC working group, because it's also doing science, but there's a focus on using giant machines. We will also work with the Deep Learning for Time series MLPerf working group. And I encourage your interest. We're just getting this started up. So here is an example which Tony Hay's group has just released with Yehan Thiagaleam and from the Rutherford Lab. And this has, these are some of their benchmark sets they have now on, and here is a link to their benchmarks. And we will look at these as the first ones to put into MLPerf. And these will give you examples for similar problems. I want to do the same thing for the COVID, the type of problems represented by that COVID data. And I have just starting a project with Argonne, Rutgers, and Jack Dangara and people from UT, University of Tennessee, Knoxville, which is to do the same thing with MLPerf, but to do it with surrogates, because surrogates have to be developed for everybody. All applications should have surrogates, presumably. And so we would be good to have a compendium of these surrogates where people can find examples. And so instead of having to work it through difficult, you can just choose within a few related application areas. So that's actually should start September 1 in a week's time, or less than a week's time. And so I encourage you to get in touch with me if you're interested. So that's what this is, the end of this section. And I want you to join the MLPerf Science Data Working Group, and you can contact the United Kingdom. You can work with the Surrogate Benchmark Initiative. We are also working with MLPerf on the so-called MLBox project, which is the technology to access these open source data sets, which is obviously pretty important. And you can also suggest new application areas for those time series. So the last set, which is a few minutes, is on data engineering and deep learning. And it's this red dot here. It's the stuff around the red dot, which we're going to come back to. And we just produced in my research group something called Cylon, and it comes from our struggles to understand how to link these worlds together: the scripting world, Python and R, the data management world, Java, and the high performance world, C++. And Cylon is meant to be a technology which links them together. And here is its, and we will give a little more detail on this. And the key technology it builds on is something called Apache Arrow, which is interoperable, very high performance data structure for storing table data sets. And so here's what we're trying. I should say, as far as I can see, Jupyter notebooks are going to be the universal interface, at least for a large number of problems. And that's why, and one reason I want to link the Python. So Jupyter notebooks are Python. They accept data from the Java data engineering, and then they hand it to the C++ CUDA-based deep learning. So if you want to make these Jupyter notebooks run well, we need to link these things together. And we need to do it in parallel, because already my my transformer models take many hours to run for just a small amount of COVID data. So that we'll need to use data parallel methods. They seem the most efficient for those types of problems. So this is the architecture. It has these clear interfaces. Everything is stored using Apache Arrow. And then if we need to link not only these, in the Python area, we need to link Jupyter, NumPy, Pandas. Obviously that's table-based, the modem, which is linked to Pandas as a orchestration engine. And if we look here, we list the performance of Cylon in its C++, Python and Java versions, and they're all roughly, they match each other across different numbers of workers from up to 128. And here is the join results for Cylon, which is running in C++, so it's running very fast, easily outperforms Dask or Spark for join operations. And anyway, so we're trying to take Cylon. We integrated with Twister2, which, if you like, is our high-performance version of Spark, but it also works with Spark, and use it to integrate with data parallel deep learning applications. And we're nearly finished. Here is the last slide. So I would say this whole field is pretty healthy. And sorry, and deep learning and surrogates are giving us lots of new challenges. And we have opportunities both in machine learning for HPC. Those are the various smart ensembles, surrogates, machine learning, auto tuning, and also HPC for machine learning, which is just making those simulations and the deep learning analyses run as fast as possible. It seems to me that there is an important change in the big data world. Big data only just got started maybe 10 years ago, but it's already changed from machine learning to deep learning. All the areas I work in now are not might use machine learning in that data engineering steps, simple analyses, but for the final step is almost always now deep learning. I then suggested that you really need, that there's a huge opportunity to work with industry, learn from what they've done, use their techniques, and adding surrogates and science data. And then I want to build tutorials around each of the entries in that MLPerf, including actually the industry ones, so that people can learn from those tutorials about what to do. Meanwhile, this whole discussion with the importance of industry says that we better work more with industry. We better develop, I haven't discussed this really in this talk, edge to cloud and systematic attention to HPC in all areas, because HPC there is no maximum difference in my opinion between a supercomputer and a cloud, because clouds have HPC. Maybe a supercomputer has a larger maximum simulation it can do. And I think there's all these changes which have happened over the last few years are causing some confusion. And I mentioned Cylon and a little bit Twister2, which have been carefully designed to build HPC into all these core data management functions. And so that's it. Thank you. Exciting time.
Okay. Can everybody hear me?
Yeah.
Okay, thank you very much, Geoffrey. That was a very interesting talk, overwhelming in its content. Very interesting. There is one question on Slack, and if you don't mind, I'll read it to you. It comes from Luc Bouget. He's the chair of the steering committee of Europar. And it reads, thank you very much for your fantastic talk. I'm also looking forward to understanding this convergence. I have a question about the methodology. You are considering physical phenomena where scientists studied for years or even centuries and found that they are driven by relatively simple mathematical models, such as Newtonian mechanics, etc. For those phenomena, you demonstrate that actually deep learning can do better prediction for a much better cost, which is impressive. However, I wonder whether the reason of this surprising achievement is the power of deep learning, or rather the conceptual simplicity of the phenomena and all the knowledge we have on their models. Actually, only the phenomena one could find mathematical models have been considered. As you mentioned, deep learning is very good at finding hidden variables. Maybe the existence of a relatively simple mathematical model is finally determinant in designing the right type of neural network and planning the right learning process. But what do we do with phenomena where we have no idea about any mathematical model? End of question.
I'm not certain that COVID has an obvious mathematical model. I also noted with earthquakes, we did incredibly well immediately with the earthquakes coming from mathematics. And we do not nearly as well with the model coming from observation, because it's not so obvious there is strong mathematical hidden variables there. So I think you're correct. It's very what works and how it works will depend very strongly on the underlying mathematics. And I'm not downplaying mathematics. I love mathematics. I was a mathematics major. And I think this is just a new tool, which is really striking how it can actually behave in ways that are quite different from previous tools. I think your points are all correct. They're all good things to do research in. And we can do this research by looking at different problems. Because I think different problems actually have different application areas will exhibit these issues in different ways. That's how we'll make progress.
All right. Thank you. Meanwhile, another question came in from Paul
Yeah,
Kelly.
I saw that. I have the Slack thing in front of me. This is about energy conservation. Yeah, so I agree that we did look at energy conservation. We have a paper. I didn't have to have that plot on my slides. And we don't build it in, but it is actually done as well as the energy is conserved, as well as the numerical method conserves it. But the energy conservation is, again, another important area that we could try to build it in, because you can learn anything. I told you I can learn cos theta, where theta has a daily variation. So if I can learn that, I can certainly learn something deeper like energy.
Okay. I myself have a somewhat more mundane question. I'm very impressed by the breadth of your applications. And I wonder how you pick your applications, how you get the data, and who the people are, what the people are that are interested in your results. Do you receive pressure to come up with results that people then go and use, particularly in COVID? That's an interesting question.
COVID, I'm working with a colleague at the Pittsburgh Public Health Department, and he provides me the data. And I've worked with him many years. I published a paper in 2013 with him from in the Big Data Conference on actually machine learning. That was multidimensional scaling and things and clustering. But in the case of hydrology, actually you can all that, these days, all of that work is sitting in GitHub. Okay. Because not all papers, but a large fraction of the interesting papers leave their results as notebooks in GitHub.
All right.
And so it's actually it's easier to actually, in some sense, collaborate without even knowing the people involved than it used to be, because Jupyter notebooks are so universal.
Yes. All right. I guess we're at the end of the session. It's right on time. Thank you very much for enlightening us and at the same time keeping control of the clock. And I hope to see you next year in Lisbon. Thank you so much. Geoffrey.
Thank you. Thank
Geoffrey.
you so much for the invitation. It was wonderful giving the talk. Thank you.
Yes, thank you from the organizers. Thank you to Christian for running the session, to Geoffrey for visiting